All right, so yesterday we did a little bit of work with enthalpy, and today we're going to continue with that. So the first thing that I want to ask you is, what is the value for the change in enthalpy for the following reaction? All right, so the astute amongst us might figure out that this is a combustion reaction of sorts. Okay? However, if I look in my combustion table, I don't see carbon disulfide in there. It doesn't show up, right? So, got a problem. You can't solve this just by looking at the table, okay? Now, what about if I give you all this information? Okay, well, that's great, but what does this have to do with anything, you might ask? Well, today we're going to be talking about something called Hess's Law, which is the overall enthalpy change in a reaction is equal to the sum of enthalpy changes for the individual steps in the process. Okay? So the sum of enthalpy changes for the individual steps in the process. What does that mean? Well, yeah, it'll make sense in a minute. I want you to remember these rules, okay? If a reaction is reversed, the sign of delta H is reversed. All right, we talked about that yesterday. If you have an exothermic reaction, the reverse reaction is endothermic, so the sign of delta H changes. If you have to multiply equations by an integer, you have to multiply delta H by the same integer. Okay, and we did that a little bit yesterday as well. So none of these should be new, but these are things that you have to keep straight. Okay, so here is the same problem, and I've just given myself some working space. All right, now what you want to do is you want all of these to add up to this. Okay, now let's see what I mean. All right, if I look through here, I have carbon disulfide in the reactants up here. So I'm going to look through, and there's carbon disulfide down here. But carbon disulfide is in the products of this reaction, and I need it in the reactants. Okay? And I guess the first thing that I better do, almost forgot something important here. I need to balance the equation, right? So I need 2 of these to balance the sulfurs, and that's 4 oxygens plus 2 more 6, so I need 3 oxygens over here. Okay, so I still need 1 carbon disulfide on the reactant side, so I'm going to flip this reaction, okay? So when I do that, I get CS2 liquid yields carbon, solid carbon, plus 2 sulfurs. Okay? And this enthalpy of formation now becomes just an enthalpy. And because I flipped this reaction, I have to change the sign of delta H. So that's negative 87.9 kilojoules per mole. All right. Make sure that you understand what I just did there, all right? I'm just trying to get this CS2 on the reactant side. All right? Now the next thing that I'm going to look at is the oxygen. However, oxygen appears more than once in the steps that I'm going to need to add together. So I'm going to skip it, okay? And I'm going to go to carbon dioxide. Carbon dioxide is here, and the equation is good as it's written. So I'm going to rewrite it. And one of the things that I found is very helpful is to kind of keep your arrows lined up so that your reactants and your products are all kind of in the same spot. And this yields CO2 gas. And the delta H for this is negative 393.5 kilojoules per mole. All right. Now the last thing that I need is 2 SO2s. All right, so I look down here and I have SO2 appearing here, but I need to multiply this by 2, right? Because I need 2 of these in my products, and I only have 1 in the products right now. So I need to multiply everything by 2. Okay, so that's 2 solid sulfurs plus 2 oxygens yields 2 SO2s. Delta H is going to be 2 times negative 296.8 kilojoules per mole. And if I do the math on that, that's negative 593.6 kilojoules per mole. Okay, now, if I collect everything that's on reactant side and everything that's on product side, let's see what I get. Okay, so I have a CS2 liquid plus a carbon plus an oxygen plus 2 sulfurs plus 2 more oxygens. And that's going to yield a carbon, a solid carbon, plus 2 sulfurs, plus CO2 gas, plus 2 sulfur dioxide gases. All right. Now, let's look at some stuff, okay? Let's treat this as a mathematical operation, all right? I have 1 oxygen here, and I have 1 oxygen here, okay? So, obviously, that's going to combine to form 3 oxygens. I have I'm going to switch colors here. I have a carbon here, and I have a carbon on product side. All right? If you have something that's on reactants and products, okay, within the reaction, that means that during the process of doing this overall equation, you create something and then you consume it, okay? So those just go away. And notice that the same thing will happen with the sulfurs. I have 2 sulfurs over here, and I have 2 sulfurs over here. So those will also cancel out. Okay. And then I'm left with CS2 plus 3 O2 yields CO2 gas plus 2 SO2 gas. All right. And notice that this is equal to what I'm trying to find. And that's my first check, okay? So in order to know if you've done these correctly, this has to be the case, all right? I need to make sure that I make exactly what I'm trying to find. All right? And then if I go and I look back at Hess's law, it says the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps of the process. So all I'm going to do is I'm going to take all of these enthalpies for each step in the process, and I'm going to add them together. Okay? And then delta H is just going to be the sum of these overall. And each of these has uncertainty in the tenths place. Okay? So I'm going to have to do sig figs out to the 10th place, and it's negative 1075.0 kilojoules per mole. Okay? Now, the last thing that I want to show you is you don't have to do this step where you write everything out. You can cancel stuff and look for things to combine right here in the steps. So for example, here's 1 oxygen. Here are 2 more oxygens. So I can combine those straight away. Okay? Here's my carbon that's being produced, and here's my carbon that's being consumed. Okay, so those can get canceled. Here's my sulfur, my 2 sulfurs, and my other 2 sulfurs. So those can be canceled out as well. So then I don't have to do this step here where I write everything out. I can just write out what's actually produced in the product. Okay? So this is doing a reaction using Hess's law. Now you're just going to have a bunch of example problems to kind of solidify this technique.